Hello, everyone, and welcome to Plant and Canopy 101, tracking water flow from soil to atmosphere. Today's presentation will be about 35 minutes, followed by about 10 minutes of Q&A with our presenter, Jeff Ritter, whom I will introduce in just a moment. But before we start, we've got a couple of housekeeping items. First, we want this webinar to be interactive, so we encourage you to submit any and all questions in the questions pane, and we'll be keeping track of these for the Q&A session toward the end. Second, if you want us to go back or repeat something you missed, don't worry. We will be sending around a recording of the webinar via email within the next 3 to 5 business days. All right, with all of that out of the way, let's get started. Today, we'll hear from Jeff Ritter, who will discuss the measurements you can make to understand the journey of moisture through the plant and canopy. Jeff is the product manager for plant canopy and atmospheric monitoring instrumentation here at Meter. He earned his master's degree in plant physiology from Washington State University, where his research focused on leaf-level gas exchange and the impact of plant biochemistry on the measurement of the global carbon cycle. Prior to working at Meter, he held a research faculty position at Washington State University in the Department of Crop and Soil Sciences. And so without further ado, I will hand it over to Jeff to get us started.
Hi, everyone, and thank you, Brad, for that introduction. I want to just jump right in here to this presentation. We're going to be talking about some ongoing research that we're doing to improve our measurement of water through the plant. So I apologize for the slightly saccharine title I've given this, A Plant's Tale, Tracking Water from Soil to Stem to Atmosphere. But my background as a plant physiologist means that I am always trying to keep the plant's perspective in mind when we are talking about parameters that we are measuring here. But before we jump too far in, I actually wanted to go back a little bit to my own perspective on plants and how that's changed over time. So forgive me a second to talk a little bit about my perspective on plants back when I first started graduate school. So you can see here a couple of species of interest. We're not going to be talking about these today, but these were species of interest to me when I was starting graduate school. Flavaria, tobacco, and corn. These are important species for physiological parameters and characterizing photosynthesis. And my perspective on plants on the plants at the time was, as you see here, very zoomed in on individual features of the plant. I was doing photosynthetic research. I was mainly interested in leaf-level processes. One thing that I missed was the broader context of the plant. We were doing greenhouse and growth chamber grown studies, which meant that I didn't necessarily care the water content of the soil, or I didn't think I needed to, it's just so long as it had enough water. I didn't care necessarily about the relative humidity in the growth chamber so long as it was an optimal level for the plant. But what I learned over time is this was just my perspective on what I was interested in learning from these plants and not really what's driving movement through the plant itself. So I want to make sure I'm focusing today on understanding that all the parameters that we are measuring here should be focused around the plant's perspective and what's important to the plant as it exists in its ecosystem, and how it functions within that context. We're going to be focusing almost exclusively on water and measurements of water, and some other measurements that are related to how we get at water usage in a plant. So keep in mind that water moves through a continuum out in nature. It moves from the soil to the plant, to the atmosphere, and then ultimately back to the soil. So we need to be able to measure water at every step along the way in order to truly understand what's driving water movement through that system. We're going to talk about soil and atmospheric measurements that you can make, but those tend to be easier to apply and understand in a lot of ways. So we're going to cover those only briefly. And again, we really want to focus on some plant-specific measurements, keeping in mind that anytime you're trying to make plant-specific measurements, it can be tough, whether you're talking about challenges for making point-based measurements or trying to do something that is continuously monitoring plants. It can be a challenge to apply those. So we'll talk through some of those challenges, but I want to again reiterate that this is current and ongoing research that we are doing. So I'm sure there are others out there who are doing similar research, and so I welcome any insights or potential for collaboration. Any challenges or pitfalls you have also faced. I would love a discussion there. So, in order to measure water in the plant, we have to understand where water is coming from, how it's moving, what's causing it to move. So, what I want to get at with this talk is trying to see how these drivers are related to water movement through the plant, how water in the soil and the water evaporative demand in the atmosphere is related to water movement through the soil. But for this research that we're doing, I want to give you a little bit of context as to where it is and what environment it is in. So this research is located in, we are located in Pullman, Washington. So you can see here that's in the southeast corner of the state of Washington in the United States. And if we zoom in, we can kind of see where Meter headquarters is located here on the map. And I want to point this out because this is where our test facility is located. If you look, I'm not sure if my cursor is going to show up here, but if you look off to the left of the main Meter building, this vast green area is land that we can use to put out our equipment for testing. This is our test facility down here. A couple of features of interest of this, you can see this is a train track that runs through the area, but you see a dark green line running through here. That's a little creek that meanders through. And this is a very wet area down here. We have a couple of different test sites down here. We've got some weather stations set up. There's also some very distinct ecosystems. Because it stays so wet, we get a grove of willows growing down there almost at creekside. And that makes sense if you know anything about willows. They're very thirsty plants. They go through a lot of water. But interestingly enough, there's also within 200 or 300 feet from that willow grove, a stand of ponderosa pine trees. And if you know anything about ponderosa pine, you know that they are very drought-resistant trees, and they tend to grow in very dry, hot places. They're very fire-resistant. So it is extremely interesting to see a willow grove and a ponderosa pine stand this close to each other. And the reason that they exist like this is, even though it doesn't show it in this picture, there's an extremely steep hill running from that ponderosa pine stand down to where that willow grove is. So you have these very distinct ecosystems, very different amounts of water in the ground because of this local topography. So this allows us to have a really interesting compare and contrast situation for water movement. Just want to show a couple of pictures of these two different environments. You've got the willows. This is very lush. This was taken sometime in spring or early summer. And you can see off in the distance there the culvert for the stream that runs through there. This stays very wet. I'll show you here in a minute. And then the ponderosa pine stand up on top of the hill. Even though it's very close, it is a very different environment up there as far as water is concerned. It stays very dry. So again, we've got these contrasting ecosystems where these are growing. And so if we would be able to measure water usage in trees, we should expect to see very different strategies employed in one of these plots versus the other. So this is what it looks like where one of our weather stations is located. You can tell at certain parts of the year, you can't really tell how wet it is, but if you look closely enough, there's ponding water down there by the willow for large chunks of the year, and that'll become important later. So again, we want to kind of walk through the whole journey of water in this presentation. So I'm going to move kind of quickly through the below ground and then the atmosphere side of this. So we're gonna start with the story below ground quickly. So just talking about soil for a minute, it is very important for you to know how much water your plant has access to. Remember, all the water that the plant is getting is coming from the soil. And so you need some way of measuring that. So if we're talking about building a toolkit for measuring water movement through your plant, it starts underground. It starts with having some sort of a soil water content sensor. So at our two plots, we installed soil water content sensors at different depths. Now, the depth that you install at is going to be crucial for understanding what your plant is able to see. If you are in an ecosystem that has very deep roots and you install at 5 centimeters, that's not actually telling you what your plant is able to get at. Conversely, if you have a plant that has a shallow root system and you put a sensor down at 2 meters, you're not actually seeing what the plant cares about. The plant doesn't care about water it can't get to. It might be interesting from a total water budget for an ecosystem, but as far as the plant is concerned, it only cares about water it can access. So we installed our water content sensors at the willows at 45, 90, and 180 centimeters down, with the understanding that the willow root system probably doesn't go down to 180 centimeters from most reports, but we wanted to see if we could get down below that root zone. Ponderosa pine sensors, we kind of knew going in we weren't likely going to be able to install down to below that root system, and we actually kind of we didn't exactly hit a rock, but we did hit some difficulties installing below 90 centimeters for that. So we were only able to install at 30, 60, and 90 centimeters. So let's keep that in mind as we come to some conclusions near the end, that there's probably some another story if we were able to go a bit deeper for the ponderosas. So let's take a look at just a snapshot of what some of these soil moisture data can look like. If we just look at these by themselves, there's still a lot of information we can take from what the plant is interested in. So this is just time series for the past 6 months of those 3 sensors I told you that we installed at the willows. On the y-axis is volumetric water content in meters cubed per meters cubed. So the way to read that is if you have a value of 0.4, that's equivalent to 40%. Your soil is 40% water, basically. So what you can see is that we were correct that installing at 180 centimeters doesn't appear to have any sort of movement over the course of that growing season. It seems to be completely flat, which indicates to me that that soil stays saturated throughout the year, and likely we are below the root system. So some other features we can take from this, if we especially focus on the 45 centimeter sensor, is all these different recharge events where the soil water content is going down and then all of a sudden it jumps back up. And we're able to see precipitation events in the soil in this way. And I'll show you that here after a little bit, just how closely that tracks. But you see you lose that sensitivity once we hit our late fall and early winter, because the soil just gets so wet that it becomes saturated. And so they can't take any more water at that point. The really interesting thing, though, that you see in this graph are these, as the water content is going down, you see this stair-step pattern in the water content sensor. And this is indicative that water loss is actually due to plant uptake, where we see a drop in water content during the day, and then it levels out at night when the plant is no longer uptaking water. So this tells us that at 45 centimeters and a bit at 90 centimeters, we are within the rooting zone of this willow tree, and we are able to see water loss, water usage by the tree. But the question is, can we tie that to atmospheric drivers? Can we look at that water usage by the tree and tie it directly to what's happening in the atmosphere? So we're going to jump up through the tree now, go into the atmosphere, and we'll circle back to the plant itself here after a bit. But I want to talk about some of these atmospheric drivers. We mentioned precipitation briefly. Again, precipitation is very important for that soil recharge, but the plant doesn't care where the water is coming from necessarily. Evaporative demand is largely driven by a couple of factors, including solar radiation. Solar radiation is what allows the plant to do photosynthesis, and to do that, it's got to open up its stomata to let CO2 in, and then it's going to lose water. Wind is an important factor, as it's going to affect the boundary layer and affect how much water is lost. And then relative humidity is also a really important parameter here that I don't have a cute little graphic for. For all this, you need some sort of a weather station to measure these parameters. It's extremely important to be able to put what your plant is doing in the context of its environment, being able to measure solar radiation, vapor pressure, relative humidity, and wind, so you can understand why your plant is losing water or using water. So we have a couple of weather stations down there, and the one for this study is the one I showed you earlier. I want to talk briefly about precipitation here. There's a couple of interesting points. Largely, you can see how much water we get here over the winter months. This is just rain in millimeters on the y-axis. But I want to show you how it relates to what we see in the soil and just how tightly coupled that is at 45 centimeters, at least until the winter months. And you can see every time there's a rain event, we see that soil recharge. What I want to draw your attention to for now, and so you can keep it in your mind, is this big event that happened in September. The soil down there at the willow plot was getting, for that area, very dry at 45 centimeters, down to about 20% water by volume, which, that's still fairly moist if you were up with the ponderosas, but down for the willows, that's getting very dry. And we had this big recharge event that took it up past 35 or 40% there. So let's keep that in mind. That's going to become important later when we are talking about understanding how these plants respond to atmospheric drivers. I do want to talk a little bit about vapor pressure deficit, or VPD. So I mentioned relative humidity, but relative humidity can be a tricky parameter to work with when we're talking about water movement. It's much more convenient to talk about vapor pressure of water, which is the total concentration of water in air as measured as a pressure. So vapor pressure deficit is then the total amount of water that air can hold minus what it currently has. So that difference tells you how much vapor pressure or how much vapor is going to be moving from one area to another. Easy way to think about this is when your vapor pressure deficit is high, your plants are going to be losing a lot of water. And so this is just a graph of the vapor pressure deficit over the last 6 months, and it kind of tracks exactly what you would expect. When it's hot and dry here in Pullman in the summer, we've got a very high vapor pressure deficit, and as we move into the cold and wetter fall and winter, that vapor pressure deficit drops off. So this should be a map of the evaporative demand that the plants are experiencing. If they've got open stomata when the vapor pressure deficit is high, they're going to be losing more water. So one more time, I want to overlay the soil moisture graph on the vapor pressure deficit. So here we have the amount of water that's available to the plant in the soil and the evaporative demand that plant is seeing. And so the question is, without actually making any plant-specific measurements, are there insights that we can take away from this? And I think the answer is yes, but it's a little tricky to tease that apart exactly. We do see periods with high and low vapor pressure deficit. The plant is still using water. Potentially we can tease apart how much that is being lost in the soil, but it's tricky to see exactly what's going on here just with looking at below ground and above ground. So it should come as no surprise that next we're going to kind of segue into talking about the plant itself and how we are missing a piece if we're not talking about making measurement of water in the plant itself. But measuring water in the plant is tricky. There are some ways to do it, and we'll be talking about one way today. But before we even get there, I want to talk about some other measurements that you can make kind of around water in the plant, measuring other parameters that are related to that. One of the ones that you can measure is, I've mentioned stomata a couple times now, so you can measure how open your stomata are on a plant. You can measure the stomatal conductance of your plant. And so the stomata are very dynamic. They open and close in response to environmental conditions. When evaporative demand is high, the plant can potentially regulate to use less water. Again, anytime they regulate those stomata to be closed, they aren't able to do as much photosynthesis. So a plant is encouraged to keep it open so long as they're not going to become droughted. One of the issues with making measurements of stomatal conductance, though, is that it's very difficult to make a direct measurement of stomatal conductance with something that is continuously monitoring the leaf. Typically, you're going to use a handheld point measurement system. which means every time you make these measurements, you've got to have somebody down at your field location. So we did some of that this last growing season, but again, with time and resource constraints, we were only able to make these measurements about 6 unique times. So while it is interesting data, it limits our ability to compare to our higher time or our higher resolution data sets. So this is the stomatal conductance values we got from our willow trees. We weren't able to get any from our ponderosa pine because that presents some other unique challenges. But this is stomatal conductance as measured in millimoles per meter squared second of water on the y-axis over time. And so you can see there's a trend there, but can we tie that into other parameters? What does that look like if we compare that to, say, evaporative demand? You might expect that as evaporative demand goes up, a plant might want to close its stomates so it's not losing as much water. Or conversely, you could see it the other way. As the growing season goes on and the plants are wanting to put on more and more biomass, maybe they are still in favorable conditions and they're increasing those stomatal conductance. So just knowing these atmospheric drivers, it makes it difficult to see exactly here why stomatal conductance continue to go up. One of the things moving forward I would like to do with this research is to have a better proxy indication of stomatal conductance, so we have better resolution. But for now, this is what we have. And so we can try and maybe take a step back, and instead of looking at leaf level measurements, try and look at this on more of a whole canopy level. And again, getting at canopy level conductance is also challenging. And so rather than do that, we were trying to look at the amount of biomass that these canopies were putting on over time. If you know how much biomass they're putting on, that gives you an indication of essentially how much CO2 they're having to take in, because to put on biomass, they've got to have their stomata open to take in CO2. The more CO2 you're taking in, the more water you're losing. So biomass accumulation should be correlated with water use as well. You run into the same sort of challenges, though, when you're doing these measurements. There are remote sensing measurements that you can do for what the measurement we're doing here, leaf area index. There are some challenges if you're using a satellite-based product as far as the spatial resolution you can get for a small grove or stand of trees like we're working with here. You're not going to have the resolution you need from those products. So we were using a point-based measurement using PAR transmittance to get leaf area index here. So leaf area index is simply a measure of the leaf area per unit ground. So again, the simple way to think about this is you've got leaf area index on your y-axis. As LAI goes up, your biomass is going up over the course of the growing season. So you run into some similar challenges with leaf area index as you do with stomatal conductance, although it is we were able to get out a couple more times for this. But the data show kind of what you would expect, where your pine trees started with a higher biomass in the canopy at the start of the growing season than did the willows. Remember, willows drop their leaves over the winter and pine trees do not. They are evergreen. So you would expect them to start with a higher leaf area index. And we could also expect them to end with a lower leaf area index. They don't accumulate nearly as much biomass over the course of a growing season. They tend to have more sparse canopies than something like a willow. That's exactly what we see here, with the dashed line being our pines. And it increases over the course of the growing season, but it is a flatter increase than the willows, which start low and end very high. Now, I would have liked for us to collect even more data so we could collect all the way through leaf fall on the willows, but that's a resource limitation when you're doing these sort of point-based measurements. So when we combine our leaf area index and our stomatal conductance, the trends match, which is what we would expect up through that point in the growing season. We would expect, these plants are actively putting on biomass, which means they need to continue to bring in CO2. So their stomatal conductance should match that. So that's what we see. But we still are we're still dancing around this topic of water in the plant, right? We're doing everything we can to think about water in the plant without actually measuring it. So what I want to talk about for the rest of the talk here is how we can then finally close that gap. We've talked about water in the soil. We've talked about what drives the water out of the plant into the atmosphere. And we've talked about some things that the plant can control as far as that goes. So stomatal conductance and biomass accumulation. To actually measure water in the plant, though, we wanted to not completely reinvent the wheel. We wanted to take something that we already have access to and see if it works to measure water in the plant. So we already have a soil water content sensor, and we wanted to see, can we simply stick that into a tree and measure stem water content? And we're not the first ones to do this. There's active research going on. There's been research in the past looking into topics very similar to this. And this is our addition to that. So we did this with the knowledge though that these sensors are designed for soil applications. So there's going to be some limitations there and some challenges to overcome. One of the ones is these sensors are calibrated for soil as a substrate, and wood as a substrate is very different. So we'll talk about some calibration challenges in a minute. I just wanted to show you some, just a couple of quick pictures of these sensors going in. You see on the left here, the team actually installing these sensors in the willows. We have to drill pilot holes into the trees and then very carefully insert them into the tree there. And you see how they look when they're installed in the ponderosa on the right. Circling back to the issue of calibration, I'm going to present data from stem water content, and it's going to have the default calibration from these sensors applied. So we know that the absolute numbers are incorrect. We're still working on these calibrations, and that's because it's a challenging thing to do. What we have found is that it takes a long time, and you have to be very careful about slowly drying these logs out while you're getting values from your sensors and weighing them to get the known amount of water and how much water has been lost. So there's enough difference even from one tree species to the next that you can't just have a general wood calibration for these sensors. You need to have a species-specific calibration. So part of the challenge is making sure that we have representative samples and that we can do this repeatedly in different tree species to have good calibrations. Another challenge that we run into is, you see over here on the right, you see that picture of the log where it's got the dark area in the middle. That's called the heartwood of the tree, which all the xylem elements, or at least the bulk of the xylem in there, is largely structural. It's essentially dead and doesn't transport water to any meaningful degree. The sensors that we're using have these long prongs or tines that would extend all the way into the heartwood. And even if the prongs themselves didn't extend into the heartwood, they have a volume of influence. They're measuring some certain volume around the sensor itself. So even if the prongs don't extend into the heartwood, we are still measuring some of that heartwood tissue. The problem with that is we're going to lose sensitivity in our measurement if we are including tissue that's not actively moving water. So to combat that, we took half of our sensors and we cut those prongs in half. So we have some sensors that are clipped and some sensors that are unclipped. And you can see picture on the right, that bottom sensor, it's got something scribbled on it, and that says clipped because some of those sensors that were clipped. But that means then that we need additional calibration points. We need a calibration for clipped and unclipped sensors in ponderosa and in willows. So essentially we need 4 different calibrations. So all that to say, this can be a challenging and time-consuming process to get these calibrations. And that's part of the reason why we undertook this was just for us to understand what it would take to make these measurements. Okay, so now we can talk a little bit about what the data actually looks like when you put a sensor into the stem, when we can measure stem water content. So I want to start by looking at the pines. This is both clipped and unclipped sensors, and I don't have the time to go into the sensitivity that you lose when you're using that unclipped sensor. But we do see that the clipped sensors are more sensitive to changes in water content. Again, our hypothesis is because we are not measuring any or as much of the heartwood. So we're going to exclude the unclipped sensors. It looks like my legend is mislabeled there. That should say clip sensors. So we're just going to be talking about clip sensors for the rest of the data here. And I want to talk through a couple of the things that we're seeing here, and then we'll compare that to the willows, and then we'll start getting into actual water usage of the trees instead of just overall water content of the stem. The first thing that we can see was one of the first things that happened when we installed these is we saw this big drop in stem water content when we first installed in the pines. So we immediately thought either we caught something that's happening to this tree physiologically right in the tail end, or this is some sort of a wound response. So as we've left these sensors installed, we have seen that yes, that is almost definitely some sort of a wound response when we are drilling into a tree and then inserting these sensors in there. And that's important to point out because you'll see in a second that the willows don't have a wound response that looks like that. It's actually even hard to tell if the willows responded at all to being installed in. So if you're wanting to measure stem water content in a similar way, just keep in mind that every species is going to have a different wound response. Another thing that jumps out that you can see immediately what looks like just sensor noise almost. You can see these big drops in stem water content, and we know that the plant is not going through that much water. And I should mention, again, the y-axis is volumetric water content in meters cubed per meters cubed, but that is using, remember, that soil calibration. So these trends are all going to be correct, and any differences, like if you subtract values from each other, that should be more or less correct. The absolute numbers that are going to be wrong. This wood is actually far more wet at this point than what's indicated by those absolute numbers. So that's still something we are actively pursuing. Anyway, back to my point of seeing these very severe dips in water content. One thing that should become clear fairly quickly is this is only happening when the weather is very, very cold. So when the weather gets cold, the water, at least around the sensor, is partially freezing. And this sort of a sensor is great at measuring liquid water, but it is completely blind to ice. So I decided to leave that in there, even though it maybe looks like sensor noise, because this is what the plant is seeing too. If we are interested in viewing this from the plant's perspective, we have to keep an account of what happens when it gets really cold. And so even though that water is still there, it's just frozen, if it can't move, then it's not really there to the plant. So the plant is kind of blind to that as well. So this gives us a good idea of why these plants shut down their photosynthetic machinery over the winter. If they didn't, and something like this happened, they could form embolisms in their xylem very easily. Okay, so the willows show more or less the same thing. The only difference that, there are some differences there. There seems to be even more of that issue of ice formation or something causing those sensors to dip. The wound response, as you can see on installation, is very different though. And we still need to do some more research to see if that is a true wound response or if there was something else going on when we installed those sensors in the willows. So something very important to understand, that every species has to be treated independently, and you can't just say that, this is our calibration for all plants, this is how we treat wound response in all plants. Okay. I want to zoom in just on the growing season so we can really talk about water movement, because we can exclude all the times in the winter where the plant isn't growing and it's not really transporting water. What we see right away are these fairly drastic diurnal fluctuations of stem water content. And you see that both in the willow and in the pines. And you can see it is far more dramatic in the willow than in the pines. And if you dig a little bit deeper, what you'll see is the peaks of all those fluctuations occur at night, and the minimum values all occur during the day. So what this is showing us is an indication of water moving through the plant. Now, there's obviously other ways to look at this, but one easy way to get a idea of the relative amount of water used through the plant is just to look at the magnitude of that diurnal fluctuation. So if you take the max during the night and subtract the minimum during the day, that's going to be an indication of how much water it used during the day. Again, it shouldn't be used to measure the exact amount of water used during the day. So these numbers are going to be relative, but it gives you an idea of what's driving water usage. So that's what we did. We subtracted we found the magnitude of those fluctuations simply by subtracting the max from the min. This is what it looks like on a daily basis. It's a little bit noisy with all the daily data in there. So if we instead just take weekly averages of max and min water content and find those differences, we can start to see quite a bit of a story. And I apologize if the font is a little bit small on these, but we've got pines on the left and willow on the right. So we'll just go ahead and put those together and make it a bit bigger. And you can start to see what sort of strategies these plants are using to basically survive through the growing season and then into the winter. And like we talked about before, we knew going in that willows were much more water demanding plants, and we can see that here with relative water use. You can also see that these plants more or less turn on the same time of year, which that makes sense. They are both in the same environment, and they both essentially turn off around the same time of the year, right around November, right when we start getting freezing events. The willow is slightly before the pine tree. But this allows us to see in great detail what exactly is moving through the plant. Now, I want to frame this more as far as atmospheric drivers go. So I've gone one step further and just looked at monthly averages. This allows us just to look very clearly at different parts of the growing season. So I'll just walk through this graph briefly. We've got the solid white bars are that relative water use or the stem water content difference in the willows. Then you've got the solid gray bars, which are the same value in the pines. So that's how much water they're using over a given month, a relative amount. And then on the secondary y-axis, I'm showing vapor pressure deficit. Now, you might notice that these VPD values, when I average them together, are quite a bit lower than what I was showing you before. And that's just because that's the total average for that month. So the values themselves are lower than any maximum you might see at one day, but the overall trend is going to hold true for each month. So what you would expect to see, you do see with vapor pressure deficit, that increases month over month throughout the growing season until we get basically to the middle of summer, and then it starts going down. So what we said before was that these atmospheric drivers are actually what's driving the amount of water that the plant is using. So we should see a fairly tight coupling between those drivers and the water use. So this requires a little bit more statistical analysis to see how much this holds. But what we do see is what appears to be a fairly good coupling between water usage in the pines and vapor pressure deficit. We see that increase in VPD at the start of the growing season, and we see a resultant increase in the pines. As VPD comes down at the end of the growing season, the pines don't really decrease their water use. And that's kind of as you would expect. As the evaporative demand goes down, they're actually able to open up their stomata further and further to take in more CO2, continue to put on biomass without losing as much water. So while we don't have stomatal conductance data for that period in the season, that would be our hypothesis, is that stomatal conductance actually is increasing during that time period. So that's one of the next steps of this is to get a proxy for stomatal conductance to be able to view that, what happens to stomatal conductance there. So maybe a small decoupling there from VPD. What's really interesting about this graph to me, though, is what happens in July and August for the willows. This is the peak of evaporative demand. And if we are just looking at these atmospheric drivers, it's hard to say exactly why they're shutting down and why they go down to that level. We can explain that only by finally kind of combining all three phases that I've been talking about in the soil, in the plant and in the atmosphere. So we've got plant and atmosphere here, and that explains a lot of this. But to see the full picture, we also have to bring in the soil moisture data. So what we see is that, remember I told you that the ground down there by the willows stays wet. I mean, it's essentially a marsh for long portions of the year, but that's not all year. As the plant is using water, it does eventually start dropping that water content in the middle of the growing season to, in this graph, again, we've got stem water content on the primary y-axis on the left, and then we've got the soil water content there on the right. So you see the soil water content goes from about 40 to 42%. Down in that July, August time period, it drops down to 25%, and some days we're as low as less than 20%. So the plant then has to make a decision. It's got a very high evaporative demand. Water is going down. So it actually is trying to regulate to conserve water. And so even though we don't have the stomatal conductance data to show this, we can see just through the relative water use, this plant has downregulated how much water it is going to be using. So what's happening in the pines if we put up a similar graphic with its water content, we can see kind of the same story at first where water content is coming down, but water content kind of levels out for the pines in August, and they don't seem to care. That the water usage goes down a little bit, but water content stays pretty much the same up until we get into November, December, and when the plants aren't using water anymore anyway. So what's going on here? Well, there's probably a couple things going on. One of them is harkening back to when we talked about getting your sensors at the correct depth for the roots. We obviously were able to pick up some water usage at our shallow sensor, but these pine trees have very, very deep and very intricate root systems that we probably are not accounting for. So even though we are seeing this depth flatline, there's probably other information down there that could explain that this tree still is perfectly happy with its amount of water and doesn't have to regulate its water usage at all past August. And the last thing I just wanted to talk about is, again, some of the challenges of combining these point measurements with these sort of continuous data sets, and how there's a lot of power in being able to look at something like leaf area index along with water usage. And that's one thing that we are going to attempt to expand this upcoming season, is having a continuously monitored data set for biomass, because another really interesting takeaway here, let's ignore the pines LAI for now. If you look at the lighter green dashed line, that's the willows biomass accumulation, that the willows LAI, it continues to go up even as it's downregulating its water usage. So this plant, it knows what it's doing. It's not stopping all activity. It's saying water's going down, there's a high evaporative demand, I need to downregulate my stomata, and I'm going to keep chugging along. So really being able to understand what the plant is doing and what it's going to be doing moving forward, you need some combination of all these things to get a full picture. So that's really all the data I wanted to talk through today. One thing that we need to do moving forward is just get more sensors out in the trees to see what's valuable to have out there, what maybe we don't need to have. But one thing I'm really interested in doing is taking the step from water content to water potential. I haven't talked about water potential in this in this talk at all, but it's really important and interesting to be able to talk about not only the amount of water in the soil and in the stem, but also the energy status of that water, how it's going to be flowing, and ultimately water potential is a better indicator of how the plant sees water. So if we're talking about something from the plant's perspective, water potential is crucial. I already mentioned some ways at getting at stomatal conductance. One good indicator of stomatal conductance is canopy temperature, and that's something that you can do using more remote sensing methods rather than a point-based system like we've been doing here, using canopy temperature to get at how your stomata are opening or closing. As they close down, your canopy temperature is going to be increasing in the middle of the day. And NDVI is also something I didn't really mention, but you can use NDVI as, you don't have to make point measurements with NDVI sensors, and you can get at a proxy for biomass accumulation. So these are all ways that we are wanting to expand this, and I'm excited to do that and see where we're able to take this, at least for a forest application here. And we also are still working on that species-specific stem water content calibration to get those numbers finalized. So in conclusion, I just kind of want to reiterate that anytime we are making measurements, because we are interested in plants, whether we are doing research or we are growers or whatever, we need to keep in mind that we need to be measuring those parameters that are most important from the plant's perspective. And we need to be measuring them in a way that takes that into account. So we need to understand the totality of how water is moving and why it's moving through the plant and how it does. So we need to measure where the water is coming from, how much is there, what's driving it through the plant, and then also how the plant is responding to that. So I thank you guys a lot for attending, and I am open to taking any questions.
All right. Thanks, Jeff. So I think we'll use the next couple minutes. Looks like we probably don't have a bunch of time to take a lot of these questions. There are a ton of questions that have come in. So just off the bat, I will let you know we will not get to all of your questions. But if you do enter in your questions, we do have them recorded, and someone from our meter team, it might even be Jeff, will get back to you and answer your question directly via the email that you registered with. So please enter and submit any questions that you have, and we will be able to get back to you if not live here. All right. So first question. Actually, there's a lot of interest, Jeff, in stem water content. It's a kind of a novel application of some of the stuff. For just really quickly, for those that do have some interest in this, we did release a recent podcast episode with a researcher who is dealing with stem water content on our We Measure the World podcast. So I just want to quick plug for that. But a lot of questions here, so I wanted to cover that really quickly, and then we can move on from there. This first question is asking if we have implemented, or not we, but if you or anybody who's doing this has implemented any practices to reduce the chance of pathogens getting into the vascular system as we add the sensors there.
That's a great question, and the answer is no, we haven't. So this is something that we have only started doing, and so any sort of introduction of pathogens or even further protections to keep rainwater off the sensors from influencing that, we are still exploring that. It is something where we have talked about, at the very least, finding some way to seal up the entry points to prevent that. But I'm definitely open to any insight you all plant pathologists might have there.
Do you think this practice of putting the sensors into the stem would be applicable in tropical ecosystems and environments? And we're using them here, what we've seen here in temperate zones. What would be the differences or similarities you might see there?
Yeah, I absolutely think that it is applicable in, the only challenge really is being able to put these in the species that you're interested in. If you are interested in a species that's got a smaller stem, these particular sensors might be too big. And so that's something that we would have to think about down the road. But as far as different ecosystems, I don't see any reason why they wouldn't work in a tropical ecosystem or anywhere else. You actually are going to get some pretty interesting data, being able to just look at what sort of seasonality you do see in water usage. Obviously here on the Palouse, we see very clearly defined seasons, and we see that in our stem water usage data, and we can see when it drops down to zero. You're not going to see that in a tropical environment. obviously, but there's still a lot of insights you can take as to, I put these sensors in this tree and it went down during this period of the year, and I don't see anything going on in the environment. What else is this tree seeing?
Is there a way to account for, or how do you account for reverse flow in tree stems, especially at night?
Yeah, I mean, it's something that the way that we are looking at the data here is kind of a coarse look just at the max and the min. So any sort of reverse flow is going to be caught up in that. And that's why I was saying this shouldn't be used to calculate the total amount of water used by the plant. I mean, also the plant is actively drawing up water during the day, and it comes to some maximum at night. But that doesn't mean that you can say that, the max minus the min is going to be the total water usage. So I think it's probably a little bit too coarse to directly account for things like that, at least for our first rudimentary pass through the data. So yeah, you would need some other method if you were wanting to parse out into effects such as that.
Final stem water content question, and then we'll move on to a couple others. Last one, when taking the readings in the trunks, did the prevailing wind direction make a difference? Did moisture content make a difference on different sides? So also when it comes to heating from the sun or other things like that, do you take that into consideration?
So as far as the prevailing winds, it's kind of a unique area. Because it's down in this valley, we really only get winds from two directions, and it's really only one direction during the day. So it's not something that really drives much change there, but it would be interesting to look at that in other sites. If you've got, as wind direction changes, are they bringing different weather parameters, and can you see that in the stem water usage data? Again, because of kind of the unique habitat, especially that the willows are in, that's not something that we can tease apart there. And I didn't talk really about the solar radiation data in this. It's still something that we've got to dive into a bit, but these sensors are under the canopy. So the sensors themselves don't see very much solar radiation. So it would just be the leaves at the top of the canopy and then driving the water usage in the stem.
Finally, I'm going to give you 2 minutes.
Okay.
There are several questions asking about water potential. You teased talking about water potential.
Okay.
Can you give just a 2-minute kind of overview of how water potential might be involved in studies of water use by plants?
Yeah, so ultimately, it is the water potential that drives how water is moving. So just because the pool size of water, it's hard to tell how it's moving. Water potential is more of a direct measurement of where that water is moving. So we can measure the water potential in the soil, and we know the water potential in the air is very, very low. And so water potential of the of leaves is something that people have made measurements of for a long time, but that tends to be with destructive measurements. You can do stem water potential, but in very small stems and pressure bombs. But actually being able to measure stem water potential in a tree trunk is a difficult thing. And there are tools out there to do it, but they tend to be very challenging. So one of the things that we are wanting to do is to take a soil water potential sensor and stick it into a tree and see what happens. And I can't guarantee that we will get good results or even results that I'll want to necessarily share, but that is the next phase of this, is just seeing how far can we push this, how far can we take sensors that we designed for something else entirely and just stick them into a tree and see what happens. So yeah, that's as far as water potential goes, that's kind of the next step and the thing that I'm most excited about.
Well, that's going to wrap it up for us today. Thank you, everybody, for joining us. Thank you for staying a little bit over. We hope that you enjoyed this discussion here. Thank you again for all of your great questions. There were a ton of questions that we did not get to, but we will through email. So stay tuned for those answers to come through, either from Jeff or somebody else from our Meter Environment team. Also, please consider answering the short survey that will appear after the webinar is finished, just to let us know what types of webinars you'd like to see in the future. And for more information on what you've seen today, visit us at metergroup.com. Finally, look for the recording of today's presentation in your email and stay tuned for future Meter webinars. Thanks again, stay safe, and have a great day.